Hello and welcome to the lecture Generative Adversarial Network Part 2. In this lecture, we are going to discuss the advantages of GAN and the problems of GAN. Then we try to find out what are the solutions of these problems with GAN, namely the mini-batch GAN and what is the train GAN, or popularly known as WGAN. Then we are going to discuss two variants of GAN. One is conditional GAN and one is cycle GAN. Here we are going to discuss about what are the advantages of generative adversarial network. As we have seen before that GANs can generate extremely realistic data because it has a generator as well as discriminator, and discriminator helps generator to generate the data or synthetic data that is very close to the real data. That's why the ultimate product what the GAN is going to generate is very close to the actual data or realistic data. It may be images, audio, video, text, etc. whatever. It produces sharp, detailed images due to the same reason. And it also captures complex pattern in data. The major product of this GAN is DALL-E of OpenAI. Sometimes GPT-4 also uses some GAN concept. Now, another very important advantage that in this generative model, it doesn't require explicit probability modeling. So, as we discussed earlier, in generative adversarial network, we use the implicit density estimation. So, training does not require directly involves MLE, maximum likelihood estimation. It learns directly through adversarial training. That means it basically used a game-like situation, min-max game between generator and discriminator. Okay, generator and discriminator are competing to each other to get more realistic data. Next, one of the major advantages of GAN that it is supervised, it is unsupervised in nature. Why it is important? As we know that in our supervised learning paradigm, there is a lot of requirement of annotated data, which is very costly. But GAN is itself unsupervised, so annotated data is not required. So GAN can learn from unlabeled data, which is valuable because labeled data sets are expensive and time consuming to create. So GAN can supply a lot of annotated data for different supervised models, but itself is unsupervised in nature. Again, GAN is somewhat resilient or prevent overfitting, because if we recall the GAN architecture, you can see the generator never see the actual data, the true data distribution. Rather, it generates data from latent variables or random variables. So it increased the generalization, so it robust to overfitting. Again, for data augmentation task to increase the data set size and balanced class distribution, again can be used to generate synthetic image or other modalities of data synthetically. So these are the major advantages of GAN. Now we are going to learn what are the problems with normal GAN. There are two major problems. One is non-convergence, another is mode collapse. Let us understand one by one. So as we know that GAN involves two networks. One is generator that tries to create fake data, and another discriminator tries to detect real versus fake. These are two major neural net that is competing to each other. More technically, this generator and discriminator play a minimax game, as we discussed in the loss function and the training of the GAN. This minimax game, when it is going to converge, it converges to a Nash equilibrium. It is not a standard optimization problem. Unlike normal neural networks that minimize a single loss function, GANs optimize to competing objects at the same time. So that we have to understand that generator, when generator optimize, then when it fools discriminator. When discriminator is optimized, when it can detect real and fake. So there is some problem. So their objective is contradictory, or it is competing to each other, and that's why this what actual as a whole GAN is going to target, that it's kind of a minimax game, and that is basically kind of convergence, you can say, Nash equilibrium of a game. Okay, so now this stochastic gradient descent that has been used for this converging or optimizing was not designed to find the Nash equilibrium of it. Actually, it is basically used for a standard optimization. So it might not converge to the Nash equilibrium at all, and that is the reason that GAN may not always converge very well. It is one of the inherent problem of the GAN, and this is called non-convergence. Another major problem is mode collapse. What does this mean? The generator may produce the limited varieties of outputs. Okay, that means it output if it's a phase, the similar phase or redundant type of phase very often. They basically ignore parts of the data distribution. For example, if it trained on phases, that is image, you can see it might generate very similar looking faces repeatedly. You can see that these faces are somewhat similar. They may be good in quality, more realistic, but variety is very less. Okay, so it very much redundant, and this is called mode collapse problem. Now we understand that mode collapse is a serious issue, and what are the countermeasures? That means how to solve this mode collapse problem. So the first idea is mini-batch GAN. Now, at mode collapse, what is happening? Generator produces good samples, but a very few of them. They are repeating the similar samples. But discriminator can't tag them as fake, as the discriminator judges each sample independently. And these are the good samples. They are basically very realistic in nature. So sample by sample, when they are judging, discriminator find it is very close to the real sample, so it can distinguish well. So in mini batch GAN, what people basically proposed, that discriminator looks at the entire batch instead of a single examples. So there is a group of these generated samples, and discriminator looks not a single sample at a time, rather it looks the entire batch. And discriminator compares samples within the same batch. If it find that whether generated samples are too similar, then it flags a error, or this penalize the samples. So discriminator, in other words, discriminator checks whether generated samples are too similar to each other. And if there is a lack of diversity, if they are too similar, it will mark the example as fake. So objective function is bit different than normal. And if it is so, definitely generator will be forced to produce the diverse samples. Okay. So this is the basic ideology of mini-batch GAN, that how it helps to produce more diverse sample and will essentially solve or reduce this mode collapse problem. Now let us find how mini-batch GAN works. So it extracts feature from its sample and then compute similarity between samples in the mini-batch. Mini-batch is a small group of fake samples. And if they find that they are very similar, then they make it or flag it as a fake. So a diversity feature has been added to the discriminator, and this diversity feature of this mini-batch. And if generator outputs are too similar, it's very redundant. That means discriminator detects it and make them as a fake. So it essentially what is doing, it makes generator to produce diverse sample. Okay. So in this way, the mini-batch GAN works. Our next idea that is proposed in 2017 as Warzertein GAN, or popularly known as WGAN. It's another variant of GAN proposed to improve the training stability and reduce the problem like mode collapse and non-convergence. As we discussed earlier, there is a problem with GAN, that mode collapse, non-convergence. Original GAN used the Jensen-Shannon divergence to measure the difference between real and generated distribution. As we discussed, that there is a real distribution, that P data, and there is a generated distribution, P of G. What was our target? That these two distributions become very close. But how we have to know that closeness, how we measure the closeness? In GAN, we use the normal GAN. The Jensen-Shannon divergence is used as a measure to measure the distance between this real distribution and the generated distribution, or you can say fake distribution. The problem of this divergence, this metric, if distribution don't overlap, the gradient match. Because of this, training become unstable and generator may collapse to a few modes. So this is the one of the major problem. In WGAN, it replaces this Jensen-Shannon divergence with Wadzer-Turing distance, also popularly known as Arts-Mover distance. What this distance measures? It measures how much effort is needed to transform the fake distribution into the real distribution. Okay, that is very important. That I repeat, how much effort is needed to transform the fake distribution to the real distribution. They may not overlap, but still it is tried to measure this effort. So unlike J's divergence, it provides meaningful gradients even when distribution do not overlap. And that is the main tricks. So loss correlates better with the sample quality. Now how this WGAN helps with this mode collapse? So as a result of what we have said previously, WGAN provides continuous smooth gradients. Even if the generator outputs poor or limited samples, the discriminator still provides a useful feedback such that generator keeps improving instead of collapse. So it helps in this way, this mode collapse problem. It also encourages better distribution coverage, as this W distance or Wadzer-Turing distance penalizes the missing modes and poor convergence of the distribution. As a result, if generator collapses to a few modes, the distance remains large, and the strong gradient pushes generator toward missing regions. So the diversity increases. Okay. Now we are going to discuss another variant of GAN. It's called conditional generative adversarial network. In short, CGAN. A conditional generative adversarial network is an extension of the original GAN where both generator and discriminator are conditioned on additional information. This is the definition of CGAN. in this lecture we're trying to understand what it is. So as of now, what we have discussed, in standard GAN, a normal GAN, generate random samples. There is no control that what samples it generated because it is generated from the random noise. The input to the generator is the random noise. It's a latent random variables. So we have no control over what it is generated. Now in conditional GAN, generates sample based on some given condition. How condition is given, then we'll see later. But there is some sort of condition is imposed. Under this condition, this generator generates the new samples. So definitely here we allow controlled generation. And we'll see there is a lot of applications in different computer vision, natural language processing fields of this conditional GAN. Let's see. Now here we have designed or we have drawn the normal GAN and the conditional GAN. What is the basic idea? Now here you can see this is normal GAN. We understand very well that this is latent random variable. Now it is a random variable. There is no control. It's a random. Now G is what? This GG. These samples we have no control over it. Whatever. Only it is on the adversarial. But from this Z to ZZ we have nothing to say. Okay. On the other hand, in conditional GAN, now you see there is a condition being imposed to this generator. Now what this condition is, maybe some sort of label, some sort of images, or sort of data instance, whatever, that we'll see later, but some condition is there. So it generates the sample given the condition. That is very important to understand. Even these real data are based under this condition. And that we'll see that why we saying this. Now discriminator also discriminate real and fake data when is X given C and Z and rest are same. So by virtue of this architecture you can understand how this conditional GAN is different than the normal counterpart. Now what is the loss function of normal GAN? As we know that expectation of X p data X of log of dx plus expectation of z of pz log of 1 minus d of g of c. That is the normal GAN, and this will minimax scheme. For our generator we minimize this, for our discriminator maximize this. This is the normal GAN that we have discussed earlier. Now in conditional GAN we put a condition here in both the cases. This is a real data, this is for generated data, because generator is now generating the samples under given condition. Okay, so this is the condition. Okay. Now in conditional GAN, now this is the one very good example. Here this is paper from ISO. In this conditional GAN, you know, this is a kind of image translation kind of application, and how conditional GAN is being used. Now see these bag images. Now this is just a kind of condition or precondition is being added. Now why I said that it is kind of condition? Now see, the real data set is also following this. maybe it a different kind, but some small differences. But and here generator is generating not from a random noise, rather there is some condition, some clue, something is given based on this generator. Now still it is a predicted sample, or you can say generated sample, and it is a real sample. And next thing is same. The discriminator is basically going to real and fake. What are the discriminator is, and this the adversarial loss is coming. Rest thing as same. But the GAN is designed based on some condition. This is a very seminal paper. This has led on 2017 condition adversarial network. Okay, so that is, so another kind is called peaks to peaks conditional GAN. So when a conditional adversarial network, this CGAN, is called peaks to peaks, that learns a mapping from input image to output image, as described in the image to image translation by a slide that we have. Now the thing is that, so this is one kind of image, it is a sketch kind of, and it is a normal image. So it's image to image translation. This is input and output is very close to the real. So in peaks to peaks scenario, or kind of described, we find it is not a very much application specific, this peaks to peaks concept. It can apply to a wide range of tasks, including synthesizing photos from label maps. So this is input, this is the condition, this is the output, this is photos. Generating colorized photo from the black and white images. Now black and white images may be condition, colorized images generated or synthesized. Turning Google Map photos to aerial images. So lot of things can be done. Even that what we have discussed, the sketches into photos. So this peaks to peaks conditional GAN is a very interesting. And as we discussed earlier, that before this peaks to peaks, the CGAN was first proposed by Smith and et al. in 2014, that we have discussed here. Okay. Now this is a very good example of peaks to peaks conditional GAN. That image to image translation with conditional inversion. Some very interesting examples. Day time to night. Okay. To edges to photos, some sketches to photos, some grayscale image to color image, or black and white image to color image. So you can understand that a lot of things can be done by this, using this peaks to peaks conditional GAN. That is used image translation kind of, a lot of things, domain adaptation kind of, lot of things. Now we are going to take another example in peaks to peaks conditional GAN. Here this is also an image to image translation. You can say there is a Sue image. Here we can, the concept is very similar, that this is condition, some sketch images, and we want to translate this actual images, and there may be fake, real, so discriminator take a call. But there is a question here. Question is that in this kind of image to image translation, we require a paired images, the sketches, the corresponding. the shoes. So this is required for this kind of model. Now see, this pairing of images that is required in traditional image translation, paired data, it often unavailable. And that is one of the disadvantage of that image translation by this normal conditional GAN. Now introduce another very interesting concept called cycle GAN. Cycle GAN is a type of GAN designed for unpaired image-to-image translation, where this kind of pairing is not available. So this pair, sketch and real photo, this pairing is not available. So cycle GAN learns translation between two domains in some lecture. There is a concept of domain adaptation. So cycle GAN is basically translate between not two images, better to say two domains without pair examples. Let's see this very interesting concept. Now here you can say this is a zebras, this is horses. So there is no, this is a kind of domain. It will look somewhat similar, but if you can say this unpaired kind of images, this is summer winter, maybe these are the kind of thing. So these are two domain now. Maybe this is summer domain, winter domain, this is zebra domain, this is horse domain, something like that. And even if this kind of this something orientation wise it is somewhat, it looks similar, but if it is still completely unpaired, then how to handle this? Okay. Now cycle GAN learns two mappings between two domains. So domain A, let this zebra, and domain B, let horses. So cycle GAN has two generator, two discriminator. Let GA to B, this is generator 1, this is GB to A, another generator, and two discriminator D and D. Now here we try to understand what are the basic designs. This G to A, GA to B is basically the first generator. It takes the input of the real zebra images and try to generate fake horse images because it's a generator and it's a kind of condition. Then another generator, they input this fake horse images and try to reconstruct this real zebra images. Reconstruct zebra images. So another two discriminator is there. One discriminator A, this is for domain A discriminator. Okay, so that is input is real zebra images and reconstructed zebra images, and they find the reconstructor and backpropagate to this so that it learns well. Another kind of discriminator here, that is, there is a fake horse image and there is the real horse images, that between these two is real image and fake image, and this adversarial loss that's going to drive this. So exactly this is the architecture by which this cycle can. Okay. Then this kind of pairing of this is not required, because these are no way connected. Okay, let's say example check. This is a real image domain, so these zebra images. This real zebra images, and this GAB that generated is basically fake horse images. That is to this GB of A that reconstruct the zebra images. This and this will go into a discriminator and to this L2 loss, and that will come here, that is reconstructed. And there is a this horse image is fake, and there is a real horse images. That way DB, it is discriminator in domain B, that real and fake, and this adversarial loss come. So by this architecture, cycle can generate the or translate one image to another, which is not paired. Okay. So in this lecture, what we have learned, first we understand the advantages of GAN and the problems with GAN. Then we come up with some countermeasures as minibus GAN and Warszawa GAN to solve these problems, mode collapse and non-convergence. Then one variation of GAN is conditional GAN and cycle GAN discussed. In next lecture we start variation. Thank you very much.